Welcome back. Today we're going to continue looking at PDEs. We're looking at the Laplace equation, rectangular boundary. Today, as you can see here, we have all Neumann boundary conditions, or all derivative boundary conditions. So, for example, remember the heat equation? When we had derivative boundary conditions, that meant the ends were insulated. We had no net flux on any of the surfaces. So that's what this means. We have no flux on the surfaces. So looking at part A here, it gives us the answer and it wants us to find the answer. So it gives us the fundamental set of solutions right here for both u0 and u of n. So let's take these boundary conditions, let's rewrite them here. This would be u. Oh, I'm looking at the wrong one. So our boundary conditions were given here. We have x prime of 0 is 0. Y prime of 0 is 0. And we have y prime of b is 0. Right? Remember, when we separate the variables of the wave equation, we end up with, you should all be very familiar with this by now. So when we do our boundary value problem, you can see that we need to use this with these two right here, right? So let's go down here. Step 2, boundary value problem. This is step 1. So it wants us to stop at the fundamental set of solutions. Okay. Let's do the case for when it's less than 0. I already know this is going to be only trivial solutions, but let's go ahead and do it this one time. If this is less than 0, this is equal to negative mu squared. What's the formula here? This is going to be positive mu squared y. Solve the characteristic equation. I'm just going to go ahead and take the square root. Right? This is all second order ODEs. C1e to the mu y plus C2e to the negative mu y. Take first derivative because we're going to need it. Right? Oh, I forgot to put the mu there. Yes. Okay, then we could go ahead and do y prime of 0 equals 0, right? Yes. So we're here. This would be mu c1 minus mu c2 equals 0. We get c1 equals c2. Let's go to the next one. Y prime of b equals 0. I'm just going to rewrite this so I can use it. Mu y. Okay. So y prime of b would be mu. Come on. C2 e to the b mu minus mu c2 e to the negative b mu. Right? So now what do? This is equal to 0. We look at this, we're like, what can we take out here? We can factor out a mu c2, obviously. Mu is going to be a constant. C2 is a constant, but we don't know what it is. Oh, what am I doing? I'm supposed to take that out. e to the negative b mu equals 0. So if mu is equal to 0, then this equation would be equal to 0, right? But if this is 0, then lambda is not satisfied because then it's less than 0. I mean, it is 0, right? Which is not less than 0. So that would not work. So that basically tells us that this right here, mu has to be greater than or less than 0 in order for this to even satisfy. So that tells us automatically that C2 has to be 0 for this case. Because for any value of lambda less than 0, mu in here, we're going to get C2 equals 0, right? If C2 is 0, we know C1 is 0, then Y is going to be C1 that plus C2 that, this right here, right? That is 0, that's 0, Y equals 0. Only trivial, right? So now, where was I? Okay, yes, let's look at the next case. Now we know, because it gives us this, oh, whoops, go back. How do I go back? Okay. It gives us this. We know that this is going to be one that's going to work. Okay, so for this case, remember it always, well, we're gonna be left with this. Repeated roots, reduction of order. Y prime of 0 equals 0, so that's C2. But this is prime, so yeah, Y prime is equal to C2. That's equal to C2, which is equal to 0. C2 is 0. So we're left with Y is equal to C1. And in this case, Y prime would be equal to 0. So what could we do in this case? Nothing, right? Nothing we could do here. Excuse me. So I don't know if you remember the one not too long ago we had a case like this. So this tells us that we can't ever know what C1 is. This problem we have no way of solving for C1, but we can solve for C2. So we know that Y is equal to C1. So what we do is we're going to define Y sub n equals C sub n, and then we're going to call, well actually no, this is for n equals 0, right? So then we're going to define Y sub naught is equal to C sub naught, just rewriting that, for every n equals 0, right? So this would be our first eigenfunction. This is when lambda is not 0. Right. So now we have one case left, less than, I think, no, greater than. So for this case, we have lambda equals mu squared. So then R is going to be plus minus mu I, lambda I, right? So this is the imaginary case. Cosine mu I plus C2 sine mu I. We have Y prime is equal to negative mu C1 sine mu I. Oh, whoops. Plus mu C2 cosine mu I. We can now use our first condition, Y prime of 0 equals 0. Whoops. We're going to be left with mu C2 is equal to 0. C2 equals 0. Right? So now let's solve for y prime of b. As we can see, that's just going to be b mu, right? Or mu b, and then equals 0. So then for this one, obviously it's going to be non-trivial, so we can solve for this. Remember, sine of 0, it has to be some form of n pi. So b mu has to be equal to n pi. Mu is then equal to n pi over b. So then our lambda n is positive n squared pi squared over b squared. Our eigenfunction is, sorry, this is y. C sub n sine, no, cosine C2 0. I'm looking at this up here. Cosine of mu, what times y? Right. So that's that. Step 3. Solve for x. We had this equation here with the other one. We had this boundary condition. Let's go ahead and solve the characteristic. Are plugged in for mu. C1 x is equal to C1 e n pi b over x plus C2 e negative n pi over b x prime. We just multiply it by this. Plus, minus right? You can apply our boundary condition of 0. So this is n pi over b c1 minus n pi over b c2 equals 0. And then from this, c1 equals c2. So then, yeah, we can plug that in for x then. So we can, I'll plug in for c1, so then I can pull out a c2 from x. And then we're left with e to the n pi over b times x plus e to the negative n pi over bx. 1 second here. Let me copy this right here. So we see we have the two cosine cosh, right, of h. So we can plug in for that. So that's x equals c2 times 2 cosh of n pi over b times x. So then x, yeah, remember the 2 combines with the constant. So I'm going to go ahead and I'm going to write this in terms of n now. Cosh of n pi over b times x. So that 2 combines with the constant. Now, the step 4 is the fundamental set of solutions. So remember, we define, and this would be xn tn, right? So then u of 0 xy is equal to x naught times t naught. Wait, where am I getting T from? I'm thinking of heat. It's Y. Why not? Yn. What is Y naught? We know Y naught is C naught, right? What is X naught? Plug a 0 in for N here. What's cosine of 0 is 1. So then we can see that that's just a constant. Where's my... We can see that that's just going to be equal to a constant. So that's C naught times C sub n. I'm going to call it C naught prime. Even though, what did they have up here? C naught. You get the idea though. U n x y is equal to C sub n cosh n pi over bx times cosine n pi over by. This would be prime as well, because the constants combine from the multiplication. This is our fundamental set of solutions. This is the answer to part A that it wanted. Right? Cosh times cosine. Yep, perfect. X and Y. X and Y. Perfect. So now, what does it want for part B? Let's give it a read. By superposing the fundamental solutions of part A, right, formally determine a function u satisfying the non-homogeneous boundary condition, of course. We know how to do all that. Note that when u of x, ay is calculated, the constant term is eliminated. So first, let's just superpose the fundamental solutions to get our general solution. A general solution would be uxy is equal to c naught plus n equals 1 to infinity of cn prime cosh n pi over b x cosine n pi over b y. It's just a general solution. That's a superimposed fundamental set of solutions. So now it wants us to use the initial condition. Well, not the initial condition, but that other boundary condition that's left. This one here. To satisfy the to determine a function u. Just note that when u of x, ay is calculated, so let's do that. We have to do that. So it wants us to find ux of ay, so when x is a, c naught prime plus n pi over b times a times cosine n pi over b times y. Oh wait, sorry, that's uay. Now we find uxay. That c naught goes to 0, right? So it's 0 plus. I think that might be what it was talking about. Oh, I get it. I think I get it. Maybe. So this will be n pi over b times c sub n prime no, actually this would be sinh now, right? N pi over b times a times oh, I forgot. This is with respect to x. This is with respect to y. Times cosine n pi y over b. We know this is equal to f of y. So let me read part B again. Note that when uxay is calculated, the constant term is eliminated. Yes. So then we can't determine C naught. That's exactly what I was thinking. Yeah. Furthermore, it must be possible to express... By the way, this is my first time doing this problem. You can't tell. It must be possible to express f by means of a Fourier cosine series of period 2b, right? Which does not have a constant term. This means that is a necessary condition for the given problem to be solvable. Finally, note that C naught remains arbitrary, and hence the solution is determined only up to this additive constant. This is a property of all Neumann problems. So basically what it's saying is we just keep the C naught there because it's arbitrary, and we solve for Cn the same way we've always have been. They just word it really confusingly. So we solve for Cn prime. So we're going to mark C naught as arbitrary. Cn prime is going to be, see we have this cosine here, this sinh here. So it's going to be C of n times sinh, so and it's actually going to be n pi over b times sinh is equal to the 1 over L, which would be b in this case, I believe. Or is it? Is it A? Which side is that on? The Fy. Fy is on 0 to b. So this will be 2 over b integral 0 to b f of y times cosine n pi y over b dy. So then C sub n prime is equal to 2. Well, that b is going to disappear, so we're left with 2 over n pi times over n pi. So this can become n squared pi squared, right? So that's going to be our answers, basically. This. So if I'm going to plug this in the uay, you're just going to keep this. Sorry, not this one. This one. This is our solution. You're going to keep the C naught there. It stays there. Plug in. And then this is our answer. So it's the same method of solution that we've always had. It's just that the fact that in this case our little mock, what I call them, mock initial condition, that other boundary condition, is also Neumann, which is the first time we're seeing that. So C naught will be arbitrary for this. Okay. So that's the answer. Next, we have one more video for Laplace equation on a rectangle. The next video is going to be a Robin problem, first of its kind, that we're going to see for Laplace. We have mixed boundary conditions. So we're going to have to redo the boundary value problem again, which is fine. So hope you enjoyed this video, and I'll see you in the next one.